Tanya, how do you prefer to have just the presentation and then the discussion, or we can discuss during the presentation?
Well, if it is not anything really urgent, then I prefer to have a discussion after presentation.
Perfect.
Because sometimes people just ask things that you will show
Perfect.
after.
That's true. That's true.
So, so I was just saying that today we have a guest, Dr. Marco Stefanelli, who kindly agreed to give a presentation about a neural network-based observations operator for weather radar data simulations. It is quite a specific topic, very technical, but I hope that you will enjoy the presentation. So, I propose.
Thank you. So, very long title and boring after lunch, but I will do my best. So, at the end of the presentation, will be clear what I wanted to say in this title. And we will go through why this study, first of all, what is data assimilation? How many of you are familiar with data assimilation? Okay. 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 And the problem of assimilating radar data, a possible solution using neural networks, and a 3D VAR application. So, why this study? In the climate change era, heavy precipitations are becoming more frequent and more intense. These are generally convective storms, and the state of the art of numerical weather prediction to predict, to forecast this kind of events is still challenging. And we have also to take in consideration that the Mediterranean region is a climate hotspot. And in Mediterranean region, we are experiencing these events even more often than other places of the world. Also, Slovenia in 2023, early August, experienced important flood that killed 6 people. But in general, as you can see, Bosnia, Italy, also Croatia, RSP France, Spain on the other side. So uh, it's a problem that we cannot really forecast it correctly, these events. There are different problems, and who works with numerical weather predictions can have 30 pages of problems that why we cannot forecast correctly these events. But there is one common problem behind it that is intrinsic of the numerical weather prediction and is intrinsic in the physics there, which is the deterministic chaos. When we want to talk about the deterministic chaos in atmosphere, generally we use the Lorentz extreme model. Maybe you know the butterfly effect. These are the 3 equations that describe this convective system, which is very simple: a cold plate above a warm plate, and then convection. And these 3 equations comes from a simplification of the Navier-Stokes equations that we had in numerical weather prediction models. And here, in this part, you can see that in black, I called true, supposing that I can correctly measure without errors the initial conditions that are this one for x, y, and z. And then I can forecast using the same model, but using another observation which has an error. And the error is 0.001 with respect to the true state. As you can see, after a certain time, the 2 forecasts are on different, are capturing different system. This one is here, which is the true, and this one, the grid, is here, which is the forecast one. What we can do to try to minimize this error, we can use data assimilation. What is data assimilation and what does data assimilation? In a very simple way, data assimilation is the bridge between model and observations. You can think for this tool as observations radar data and as model ALAPAN, which is used here. and the radar data is the least one. How data assimilation use these sources of informations? You have the model space, and in the model space you have your forecast, the Aladdin forecast, which is called background. This, of course, has an error, and it is defined on a grid, on a regular grid. On the other side, you have the observation space. There you have observations, which of course has errors, and they are on a different grid in general. So in a non-uniform, I would have also to say grid. Once we have these two sources, how these two spaces can speak each other? Using the observation operator in variational data assimilation, for example, 3D var, which is the one that you use here with the Aladdin forecast. And the observation operator is generally is mapping the model space into the observation space. And we'll be clear later how this is done. What is important here is to get this, that model and observations have used to compute the analysis. And the analysis has a smaller error than the model and then the observation. So is a model state improved using observation, and it would be used for the next forecast. I don't know, here is 6 hours forecast, right? Before the analysis. Three. So you have the forecast of 3 hours, you stop, you get informations from observations, and then from the analysis at that time, with 3D var, you can forecast the other 3 hours. And this, of course, as you can get, can minimize the error due to the deterministic errors. How? Let's have an example. You remember the tree equation from Lorentz system, just get the x component, and again in black there is the true state, our target. What we can do as initial condition, we can observe it. Of course, there is an error, you see the difference. And then we can run our model. As you can see at the beginning, the error is not so big, but for example here there is a big error, and here there is a complete different behavior of the system. So let's use data assimilation. As I said, we can stop, we can observe the true state with an error, of course, at specific time steps. And then when you have observation, you can compute the assimilated state here, which you can call also the analysis. And these blue dots would be the new initial condition for the next forecast, for the next 3 hours. And as you can see, the magenta curve is more in agreement with the true state than the gray one. Of course, there are still places where this is not working. If you are interested in playing a bit with this, I wrote a JavaScript web app. You can download from my website that I will show later. But you can play with the Lorentz system and with the data assimilation. Or if you are teaching this, you can download freely and you can use with your student. There are already some questions for students or for you to drive in using it from the scientific point of view. And in this tool, you have, again, the Lorentz system. Then you can modify the parameters. Maybe you can try to follow the paper from Lorentz into sharing it. Then you have initial conditions from two curves. One you can call the true one, you decide the initial condition. The other one you can perturb a bit. And you can also use data assimilation in order to improve your forecast. And here you can change the observation step. You can decrease or enlarge it. Then you can change the observation and model error in order to see if the model is very bad, what is going to do the analysis with you looking at observation or the other way around. And so you can play with it. You can download from here, from our website. Of course, it's in work in progress, but the page there is ready to be used. let's go back to our target, which is try to improve the convective storm using data simulation with radar data. Of course, the state of the art, as also here at Hartso is doing, there are attempts in assimilating radar data. However, they showed poor improvements in forecasting the precipitation patterns. And this is reported in a very nice paper from Fabry and Meunier in 2020. And in this nice figure, you have on y-axis the correlation of reflectivity patterns, and here the forecast time. As you can see here, there is a black curve, which is radar nowcasting, an orange curve, which is numerical weather prediction, Aladdin, with radar data simulation, and numerical weather prediction without radar data simulation. Now, the first thing that we see is that radar nowcasting is better than numerical weather prediction with radar data simulation. And also, even if we are improving the forecast using data simulation in NWP, this improvement is dropping very fast in the first 2 hours. So, in the paper, there are different reasons why is happening this, but the main one is that this is happening because the data simulation of radar data actually is watching at the storm after the storm is happening. So you're assimilating, for example, reflectivity, and you are improving the variables that actually are directly correlated to it, but not the environment variables, thermodynamic and dynamic, that are driving the storm. And this is something that in this study we are trying to explore. There are different methodologies of data simulation. In this study, I'm using the 3D VAR, which is also the one that you are using with Aladdin. And how the cost function of 3D VAR looks like. There is a model term in the model space that we saw before, and an observation term. In the model term, you have the analysis vector. This is the variable that minimizes the cost function. So is the variable that you are looking for, the analysis. Then you have B, which is the background error covariance matrix. There are all the model-related errors. Is a huge guy as the of dimensionality. Maybe it can reach 10 to the 12 also. And then you had XB, which is the background state vector, so the forecast at that time. Then you have the observation term. In the observation term, you have the observation vector, temperature, or wind, or reflectivity. R, which is the observational error variance matrix. There are all the observation-related errors. And H. H is our target here. We want to improve the forecast acting on the data simulation part, not on the numerical weather prediction part. And how we want to do it, working on the observation operator, which in the applications is generally linearized around the background state, but we want to use it also non-linearized. Now, H, what does? As we said, it maps the model space, the model variable, into the observation space. Why? Because we want to compute this difference here, which is called innovation. So, think, for example, that you want to assimilate an observation that is temperature. Then H is mapping the temperature variable that is produced by the model into the observation space. It's just an interpolator in this case. What if the model has not the reflectivity variable? So if the model has not it, H could using neural network also produce the model equivalent Y in the observation space and then compute the innovation. So here is my model and observation space concretely. the red square is the observation space. Is the model space, which is Aladdin, as I said, with the resolution of 4.4 kilometers. And the observation space is the Listsa radar, and this is the entire disk of the first elevation angle, 0.5 degrees. And but I filtered on 160 kilometers, so I returned just the observation below this radius. The red regions that you see here is where the radar beam hits the mountains. So that part is actually hidden for the radar. Good. So my observation operator, my neural network that want to mimic an observation operator, gets an input Aladdin model variables provided by Ure and Neva. And these are over four pressure levels and are temperature, wind components, and relative humidity. And then we have also three surface variables: relative humidity at 2 meters, temperature at 2 meters, and insular pressure. With this in input, we want to generate radar observations. So here there is lists a radar, reflectivity in the reflectivity units. And the RES unit is trained over 4 years from 2019 to 2022 and tested over the entire 2023. So if this is an encoder-decoder neural network, what you have is that y hat, which is the generated radar reflectivity or the model equivalent one, is the decoder of encoder of x, which is exactly the nonlinear observation operator that we are looking for. So let's see some results. These are just results of the application of the observation operator. So let's get a dry condition for Aladdin. And here you have the target observation from Listsa radar. And here h of xb. Xb, if you remember, is the background, so the forecast at that time. This is, there is a perfect match, but this is easy because 90%, even more, of the data set represent dry conditions. But this is a good sanity check. Then we have broad search form features. Here you have the observation, and here you have h of xb. So temperature, wind components, relative humidity, and all the variables that I have in input on my neural network produce this. As you can see, the general features are there, but for example, this zone where there is no precipitation, actually H is producing something. And also this peak, let's say, in the observations is not present here. This is not an error because the H operator should not modify what the information that Aladdin has. It's just a mapper between a space to the another space. And here there are complicated reflectivity patterns. As you can see, this one, for example, there is an event that is happening in the west part and another one in the southeast part of Slovenia. And this one, which is h of xb, actually is reproducing something here, but is completely missing the other one here. This one, this last event, is the one that caused the floods in 2023 August. And as you can see, this is complicated for the shape, but also because there are different convective cores. As you can see, h of xb is reproducing it, but actually all the convective cores are missing. And again, this is something that should not be aware for us, because if the model has not this information, then also this one should have not. Okay, let's try to apply 3D var, and here Benedict helped me. So here we have the 3D var cost function that we saw before, but actually I decided to apply in the control vector, in the control space. Why? Because in the control space, the problem of B matrix, that is a huge matrix, can be solved using a control operator, and the control operator is the diagonal element of B and the square root times the recursive filter. The recursive filter is modeling the covariance element of B. And this is the cost function that I'm going to minimize. And V is the control variable. So let's start with the bad event for Slovenia. These two figures you already know from before. And here there is h of xa. As you can see, h of xa is closer with observations. And this is also shown by the difference map. Observations minus h of xb, which is the innovation in the y minus h of x in the cost function. And here observation minus h of xa. As you can see, the root mean square error here is 6 and here is 3.5. So it's decreased. Data assimilation is doing the correct, a good job. And here we have the increments. This is a very important part for data assimilation. Here we have the increments on the input variables. And as you can see, just observing the reflectivity pattern, the observational reflectivity units, we are able to produce increments in the environment variables that are driving the precipitation: temperature, winds, relative humidity. And also, these are located where the observations are. And this is a very important feature that we can actually observe something and correct something else. In order to qualitatively say if things are working properly, let's have a look at relative humidity at the first pressure level. There should be a match between where the increments are made positive, so increasing the relative humidity, the amount of water, and negative, decreasing the relative humidity. Indeed, what we have here the red pattern shows when the h of xb is underestimating the observations. And when it's underestimating is we have positive increments. So we are increasing the amount of water there. When is blue, here the h of xb is overestimating. And here we are decreasing actually the amount of water because the increment is negative. So a qualitative check says us that the model, that the approach is working in an appropriate way. Then let's have a look at the other three examples that I showed before. This is the complicated one where there was an event on the west part and in southernmost part. So this was h of xb, this is h of xa. And as you can see also from the root mean square error, you can see that observation minus h of xb is 6.3. And on the other side, we have 3. So it's decreased, but also the difference map shows that. Also here, we have increments that are consistent with what we are doing. Then this one, maybe you remember that was missing, this part was reproduced as precipitation where it was not, and this peak was missing. Now we have this. And the root mean square error is decreased by 5.74 to 3.2. And also the difference map says that we are improving it generally, so not just in average. Another important fact here is that, as you can see, the model here is never reproducing where the radar cannot get information. And this is another important feature that this model has. Finally, sanity check. If everything is matching the dry condition, there are no increments. And that's something also good. So that's my work. And it's difficult to ingest this in Aladdin model because Aladdin is in Fortran, of course, in the time that I have. Aladdin in Fortran, and this is the entire in Python. So in the time that I had, it's very difficult. And that's why I did not show any forecast or application with Aladdin, which I hope that can be done in the future. But the main hope is to try to improve the forecast of these convective storms events. Thank you.